everybody, it's Mrs. Cat. We are going to add to our mass 3 levels diagram that we have already begun. Now that we have some more info that we can add here. After looking at the mass and change lab, we should be able to draw some major conclusions about what happens when we have either a chemical or a physical change in the mass of that system. And it's not going to change. And that is conservation of mass. So we're going to add that to all 3 levels on our diagram, starting with macroscopic. And here's where we're going to just define this as you maybe typically have learned conservation of mass. So conservation of mass can be defined or explained as the fact that mass is always the same before and after a change. Now, this can be a chemical change, it can be a physical change, but any kind of change, the mass is going to remain the same. I don't really want us to get into the habit of when your chemistry teacher says conservation of mass, you say mass can't be created or destroyed. That to us shows us that you've memorized that concept, not that you really understand it, which is part of the reason why we're going to look at this idea of conservation of mass in all 3 levels. Okay. Now, I'm going to move on to the particular, or from, actually, let's go to the symbolic level next. And when we look at the symbolic, this is going to give us that idea that the actual mass measurement before is equal to the mass measurement after. Okay, we could show that a few different ways. Maybe we have a before and after. Whoop. Helps if I can spell. After our change, and we can put some data in here. So maybe you had 2 samples. One was 10 grams in mass that you combined with another sample that was 15 grams in mass. After the change takes place, you are going to have 25 grams after. Mass the same before and after. Now, the idea of what this looks like in particulate needs to apply not just the idea of mass conservation, but what we've already talked about as far as number of particles relating to the amount of mass. So let me switch my colors back up here. So we want to say that we have the same number of particles before and after a change. Now, as with most things that we're going to represent and discuss at the particulate level, we want to draw a particle diagram. So I'm going to keep with my examples of red particles and blue particles, but let's go with, let's go with 2 blue particles combined. Let's go with 3 of those mixed with 3 red particles, and we want to combine those. So let's say, let's put these in separate containers to make it a little easier to see. And we're going to put them into the same container. So let's see here. Let's go with physical process first. And all I'm going to do is mix them in the same space. Okay? Because I have the same number of particles in my 2 separate containers and my 1 combined container, this is showing a change in the nature of this combination. and it's keeping the number of particles the same. Now, if we want to represent this same set of particles as a chemical change, actually, let's not do them in boxes this time. Let's go with the same sets of particles, right? 3 double blue particles, 3 red particles. And let's say we're going to add these together. And this time we're going to represent a chemical change. So these particles are going to combine in a different way to give us a different substance. So let's say I want to go with my red particles are going to be in the middle, and then attached to those are going to be 1 blue particle on each side. Now, I still have the same number of particles, so that means I have the same mass, but they are arranged and combined in a completely different way, giving us a new substance. That's showing us a chemical change. Okay, so just a little bit more on how we can look at the 3 levels of chemistry in the lens of mass, our amount of matter.